Now we're going to examine what is known as the common ion effect for a solution in equilibrium. And this will take us back to chapter 15 when we talked about Le Chatelier's, gosh, I hope I don't abuse his name, Le Chatelier's principle. And in Le Chatelier's principle, you have a reaction at equilibrium and it will shift in one direction or the other. So here I have a solution of acetic acid that is at equilibrium. That is, this is the lowest energy state. The concentration of acetate, hydrogen ion don't change. The pH is constant. The concentration of acetic acid doesn't change. But we're going to change that. And what I want you to think about is this. So here is this floating around in equilibrium. I'm taking a certain amount of license. And I take sodium acetate, which is a basic salt. Hopefully you're aware of that by now. And I put it into this solution. Now, the sodium acetate is going to completely dissociate into sodium cation and acetate, C2H3O2 with a -1 charge. Now, we know that the sodium cation is neutral. It's the conjugate of sodium hydroxide, which is a strong base, so the sodium cation is neutral. But the acetate ion is actually a component in the equilibrium of the acetic acid that has ionized. And so now I'm putting in more product over here. I have an increase, and if you remember Le Chatelier's principle, reactions will shift toward a decrease and away from an increase. So the reaction is going to shift back toward the reactant side to try and get rid of the excess acetate ion. It's going to combine with hydrogen ion, which is going to remove hydrogen ion from the solution in order to make more acetic acid. The common ion effect will cause a shift in the equilibrium. It will cause a decrease in the percent ionization. So the common ion effect continued when a weak electrolyte is combined with a strong electrolyte that contains a common ion, and in the previous problem that was the acetate ion. The ionization of the weak electrolyte is suppressed. That is, it's decreased the percent ionization. So find the percent ionization of both solutions, 0.1 molar acetic acid and 0.1 molar acetic acid with a 0.1 molar solution of sodium acetate. So let's do that. Okay, so we'll start off with A, and we've got acetic acid, which is HC2H3O2. It's going to ionize to some degree. We'll get some H plus C2H3O2 minus. Now, in this case, the only interest we have in the hydrogen ion concentration is so we can determine what the percent ionization is. So we have ICE, this is our ICE table. We have 0.10 molar of this. We don't have any of the hydrogen ion or the acetate ion to start with. Our change is minus X. And over here for the product side, we're gaining a little bit of the ionized product, the ions in solution, and then at equilibrium we simply add the initial to the change line. So this is 0.10 minus X. 0 plus X is just X, and 0 plus X is just X. So what we want to do is we want to find the concentration of the hydrogen ion or the acetate ion. It doesn't really make a difference. They both equal X. And so we put together the equilibrium constant expression, which is Ka is equal to H plus times C2H3O2 minus divided by the HA the HC2H3O2 concentration. Now, I'm going to go ahead and assume that I can ignore that X It would be the difference in this particular case, because if you look at the Ka for this reaction, it's 10 to the minus 5, and this is the initial concentration here. It's 4 orders of magnitude. The difference would be if, let's say, I got on a bathroom scale and decided to, I don't know, clip my toenails. Oh, that's an awful suggestion. Okay, clip my fingernails. Or I lost a tooth. So the mass would change. It's not 0, but it's such a small amount that it's really not going to make any difference to the scale. And so I can ignore this x. So let's go ahead and solve the problem. We're going to put it together with 1.8 times 10 to the minus 5 is equal to x squared divided by 0.10. When we solve for x is just going to equal the square root of the Ka, 1.8 times 10 to the minus 5 times 0.10. And when I do that, I get 1.34 times 10 to the minus 3 molar. And that's both in H+. If I wanted to get the pH of the solution, I would just take the negative log of the hydrogen ion concentration. I would get 2 something, but it doesn't really matter. This could also be acetate ion. But what we are interested in is the percent ionization. And we get that by taking X, whatever it is, and dividing that by the starting concentration, in this case, of our acetic acid. Okay, so here we go. And then we have to multiply times 100 to get it into percent. So that's going to be 1.34 times 10 to the minus 3 divided by 0.10 times 100. So let's divide that by 0.1 times 100, and I get 1.3%. And that is typical for a weak acid in terms of its percent ionization, generally between 1 and 3%. And we've got 1.3. Let's go ahead and change it now. Let's take, and here's what's happening. I'm taking sodium acetate, NaC2H3O2. It's also 0.10 molar, and I'm dissociating it. And it's a strong electrolyte, so it's going to dissociate completely into sodium cation and acetate anion. And if the sodium acetate is 0.1 molar, then the sodium will be 0.10 molar and the acetate will be 0.10 molar. Now I can put together the same reaction, which is HC2H3O2 in equilibrium with H plus C2H3O2 minus. Initially, now I have 0.10 molar. I don't have any hydrogen ion yet, but I've got 0.10 molar for the acetate. My change is going to be for acetic acid is going to be minus X, because I have a 0 concentration of hydrogen ion so far, and I need some products here. So that means that the reaction is going to shift to the right to a very small degree, but that'll be plus X over here, plus X over here. And then at equilibrium, I have 0.10 minus X, 0 plus X is X, and 0.10 plus X here. Once again, I'm going to think about the X that I'm adding or subtracting from my starting concentration, and I'm thinking that it's minuscule, like losing some hair off of my head and having it not actually change the scale. It's not 0, My mass did change. However, it's so insignificant that it's really not going to register very much on these starting concentrations. So I'm going to ignore both of these x's just to make my math easier. All right, so now I can put it together. My equilibrium constant expression, like before, is Ka is equal to H plus times my acetate concentration, H3O2 minus, divided by my acetic acid concentration, HC2H3O2. And now I'll just plug in my numbers. 1.8 times 10 to the minus 5 equals X times 0.10 molar divided by my acetic acid concentration, which is also 0.10 molar. Now, the 0.10 divided by 0.10, those will cancel, and my X value, which does equal my hydrogen ion concentration, if I were interested in the pH, is simply equal to 1.8 times 10 to the minus 5 molar. All right, so now I'm going to do the percent ionization, do that simple calculation. We have X, which is now 1.8 times 10 to the minus 5 divided by my starting concentration, 0.10 molar, and to get it into percent, I'm going to go ahead and multiply times 100. So that's 1.8 times 10 to the minus 5 divided by 0.10 times 100, and I get 0.18%. So it's less than a percent. And that demonstrates that when you have a strong electrolyte that contains a common ion and you put it into an equilibrium solution, in this case, sodium acetate, and in the acetate is the common ion, it's going to drive this reaction back toward the reactant side, suppress the percent ionization of the acetic acid. And in doing so, it's going to drive down the concentration of hydrogen ion, which will cause the pH to rise. We can actually calculate the pH of both solutions. For this solution, the pH would equal the negative log of 1.34 times 10 to the minus 3, 1.34 times 10 to the minus 3. We know it's going to be 2 something, so negative log of 1.34 times 10 to the minus 3, and I get 2.87. So my pH here is 2.87. Okay, and if I do the pH here, this is just the pH is equal to the negative log of 1.8 times 10 to the minus 5, and that's going to be 4 something, so negative log of 1.8 times 10 to the minus 5, and I get 4.74. So my pH here with the common ion is 4.74, and the reason the pH has gone up is because my hydrogen ion concentration went down. The percent ionization was much lower with the common ion acetate. So continuing with the problem-solving strategy that we just employed, first of all, identify the weak and the strong electrolyte. Set up the equilibrium reaction from the point of view of the weak electrolyte. That's an ice table. And add the common ion from the strong electrolyte. Remember, common ions from strong electrolytes, you get a complete dissociation, as we did. The strong electrolyte in question was the sodium acetate, NaC2H3O2, And it was a 0.1 molar solution of this, which gave us 0.1 of this, but it was a spectator. We don't care about it. But we had C2H3O2 minus, and it was also 0.10 molar. That's the strong electrolyte. Maybe make sure you make a distinction between the strong electrolyte and the weak electrolyte. The ICE table is for the weak electrolyte, the low percent ionization. The strong electrolyte has virtually 100% ionization. You also need to be careful if you get something like calcium acetate, because that's got 2 acetate ions. Depends on what the salt happens to be. If this is a 0.10 molar, you're going to get 0.10 molar of calcium ion. That'll just be 0.10. We don't care. It'll be a spectator, but you'll get 2 acetate ions, H3O2 minus. That means 2 times 0.10. So you get twice as many, which is 0.20, twice as many acetates from a salt like calcium acetate as opposed to sodium acetate. So use the concentration of the common ion from the strong electrolyte in the initial concentration. The molarity of the ions given molarity times the subscript. That's in the case where you have more than one ion associated with the strong electrolyte. And then just ignore the spectator ions. These are things like sodium cation, could be calcium 2 plus, or chloride ion, or nitrate ions. These are ions that aren't going to affect the chemistry. They're not going to interact with water. They're not going to affect the equilibrium of the reaction. Okay, I think that's enough for this particular video.